You may know that there are an infinite number of prime numbers. However, that fact is for the integers and is not necessarily true for all rings, or maybe it is. I'll have to double check that. However, just because it's true in the integers doesn't mean that it's trivial to extend that idea to other rings, like the Gaussian integers, for instance. How do we know that there are an infinite number of Gaussian integers? Well, let me show you. Let me show you. Here we go. Let's let P be equal to A times B, where P is an integer and A and B are Gaussian integers. So P is an integer. Why are we saying this? The goal is going to be to show that P, not just an integer, but actually a prime, we're going to show that P is a prime integer. Rather, we're going to define P as a prime integer and show that no matter what, it will always be the product of either two Gaussian integers, Gaussian primes, my bad, or the product of a Gaussian prime and a unit. In other words, it's already a Gaussian prime, or the product of two of them. So how do we do that? Well, we're defining P to be prime. Let's just remember that. We are going to say P squared. Since P is an integer, P squared will always be positive. Also, it'll be equal to the absolute value of P squared. That's the same thing. But you know what else is interesting? A complex number, let's say C plus DI times, trying to think of letters, G plus HI, the absolute value of that is in fact equal to the absolute value of the individual things multiplied. You can distribute this. You can also just call this the normal. It's pretty easy to prove. I'm not going to do it here. So, given that the normal of P squared will be equal to the normal of A squared times the normal of B squared. What does that mean? Well, remember what the normal actually is. If we bring this back, C plus DI, just a complex number, the normal is equal to the square root of C squared plus D squared, which is a real number because these are just the components, the real and imaginary components, but without the imaginary part. So squaring this will give us an integer, which means both of these are integers. What does that mean? Well, P squared is a prime number squared, which can only be factored one way in the integers, and that is P times P, but these are both integers. So the only possible way that these can be integers and multiply together to be P squared is if they are both P, because that's the only way to do it, since everything here is an integer, right? These are not necessarily integers. These are Gaussian integers, which is a superset, but these are integers. Therefore, the normal of a squared is equal to p, but then it's also equal to the normal of b squared. So these are all equal. That's very useful. So now let's let a equal m times n. A Gaussian integer. What can we write its product as? Well, we're going to write it as m times n. If we can multiply two things together to get a, what can we say about the two things? Well, we know that the absolute value, the normal of a squared, is equal to p. So what happens if we do that here? What if we take the normal of a squared? Well, we can distribute it the same way that we did here. We can go, this is equal to the normal of m squared times the normal of n squared. Look familiar? Yes. It's essentially what we did here. And the results are the same. These are both integers. This is an integer. How do we factor this? Well, if you recall, we just showed that this is equal to this, a prime number. This is prime in the integers. These are integers. How do you factor a prime into the integers? Well, you can't, because it's a prime, which means one of these must be a unit. One of them must be 1 or negative 1. That is the only possibility. So m or n is a unit. What does that mean? Well, let's go back here. If m or n is a unit, that means it's also a unit here, which means that a can only be written as a unit times another complex integer. One of these has to be a unit, which means that a is a Gaussian prime. A must be a Gaussian prime because m or n is a unit. M or n is a unit, therefore a is a Gaussian prime. Easy, right? Okay. A is prime in the Gaussian integers. Well, if a is prime in the Gaussian integers, then so is b for this exact same reason, which means that a prime integer is always the product of two Gaussian integers unless it is already a Gaussian integer. That's the proof. So what does that mean? Well, it means that every prime number in the integers, which we already know there is an infinite number of, is either already a Gaussian prime or the product of two. That means that there must be infinitely many Gaussian primes. Why? Because when you multiply two complex numbers together, the magnitude of the product is the same as the product of the magnitudes. So for arbitrarily large prime integers, there must be arbitrarily large Gaussian primes that multiply together in order to reach the sufficient magnitude of the prime. So there are infinitely many. That's why. And it's very amazing. I did not come up with this.